Good day, everyone. Welcome to our class reporting through recorded discussion. I would like to remind everyone that this is an opportunity for us to listen, learn, and support our classmates. So let's keep an open mind and be respectful of each other's opinions and ideas. The flow of this class sharing is that after every topic discussed, the learning objectives will be answered by the reporters for you to understand well our topics. So without further ado, we are Group 11 and we will discuss Chapter 11, Running Water. Running water is the most important geologic agent in eroding, transporting, and depositing sediment. Nearly every landscape on Earth shows the results of stream erosion or deposition. And you have probably experienced the power of running water. If you have ever swam or canoed in a fast-flowing stream or river. But the vivid accounts of floods truly impress us with the energy of moving water. For example, on May 31, 1889, residents of Johnstown, Pennsylvania, heard a roar like thunder, and within 10 minutes, the town was devastated by an 18-meter-high wall of water that tore through the town of 60 km per hour, sweeping up debris, houses, and entire family. Every year, floods cause extensive property damage and fatalities, and yet we derive many benefits from running water, even from some floods. Before the completion of the Aswan High Dam in 1970, Egyptian farmers depended on silt deposited on the Nile River floodplain to replenish their croplands. In addition, running water is one source of fresh water for agriculture, industry, domestic use, and recreation, and about 6 to 7% of all electricity used in North America is generated by hydroelectric plants. Water on Earth. Most of Earth's 1.34 billion cubic kilometer of water is in the oceans, and nearly all of the rest is frozen in glaciers on land. The remaining 1 to 2% of Earth's water is in the atmosphere, groundwater, lakes, swamps, and bogs, with only a very small but important amount in stream and river channels. Nevertheless, the water in channels is, with few exceptions, the most important geologic agent in modifying the land surface. Much of our discussion of running water is descriptive, but always be aware that streams and rivers are dynamic systems that must continuously respond to change, be it natural or otherwise. For example, paving in urban areas increases surface runoff of waterways, and other human activities such as building dams and impounding reservoirs also alter the dynamics of stream and river systems. Natural changes, too, affect the complex interacting parts of these systems. The hydrologic cycle. The connection between precipitation and clouds is obvious, but where does the moisture for rain and snow come from in the first place? You might immediately suspect that the oceans are the ultimate source of precipitation. In fact, water is continuously recycled from the oceans through the atmosphere to the continents and back to the oceans. This hydrologic cycle, as it is called, is powered by solar radiation and is possible because water changes easily from liquid to gas or water vapor under surface conditions. About 85% of all water entering the atmosphere evaporates from the ocean. The remaining 15% comes from water on land, but this water originally came from the oceans as well. Regardless of its source, water vapor rises into the atmosphere where the complex processes of cloud formation and condensation take place. About 80% of all precipitation falls directly back into the oceans, in which case, the hydrologic cycle is a three-step process of evaporation, condensation, and precipitation. For the 20% of precipitation that falls on land, the hydrologic cycle is more complex, involving evaporation, condensation, movement of water vapor from the oceans to land, precipitation, and runoff. Some precipitation evaporates as it falls and re-enters the cycle, but about 36,000 cubic kilometers of precipitation falls on land and returns to the oceans by runoff, the surface flow in streams and rivers. Some precipitation is temporarily stored in lakes and swamps, snowfields and glaciers, or seeps below the surface where it enters the groundwater system. Water might remain in this reservoir for thousands of years, but eventually glacier melts, lakes and groundwater feed streams and rivers, and this water returns to the oceans. Even the water used by plants evaporates, a process known as evapotranspiration, and returns to the atmosphere. The hydrologic cycle. During the hydrologic cycle, water evaporates from the oceans and rises as water vapor to form clouds that release their precipitation over the oceans or land. Some of the precipitation falling on land enters the groundwater system, but much of it returns to the oceans by surface runoff, thus completing the cycle. And again, hydrologic cycle is the movement and interchange of water between the sea, air, and land. Evaporation is when solar radiation provides energy. Precipitation can result to rain or snow. Transpiration is the evaporation from plants. Runoff is the water flowing over land surface. And infiltration is when water soaking into the ground. So take note with the word runoff means the surface flow in streams and rivers. Fluid flow. Solids are rigid substances that retain their shapes unless deformed by a force, but fluids, that is, liquids and gases, have no strength, so they flow in response to any force, no matter how slight. Liquid water, therefore, flows downslope in response to gravity. Runoff during a rainstorm depends on infiltration capacity, the maximum rate at which surface materials absorb water. Several factors control infiltration capacity, including intensity and duration of rainfall. If rain is absorbed as fast as it falls, no surface runoff takes place. Loosely packed dry soil absorbs water faster than tightly packed wet soil, and thus more rain must fall on loose dry soil before runoff begins. Regardless of the initial condition of surface materials, once they are saturated, excess water collects on the surface, and if on a slope, it moves downhill. Water on Earth Learning Objectives 1. Explain how the hydrologic cycle works. The hydrologic cycle, also known as the water cycle, is a continuous process by which water circulates between the Earth's surface and the atmosphere. It begins with the evaporation of water from bodies of water, plant transpiration, and the surface of the Earth. The water vapor then rises into the atmosphere where it cools and condenses into the clouds. The clouds then release precipitation such as rain or snow, which falls into the Earth's surface. The water can then either infiltrate into the ground, becoming groundwater, or flow across the surface as runoff, eventually returning to bodies of water and completing the cycle. Lesson Objectives 2. Define fluid flow. Fluid flow in running water typically refers to the movement of water through a channel or stream. The flow of water in a stream is influenced by a variety of factors, including the gradient or slope of the channel, the amount of water flowing, known as discharge, and the channel's shape and roughness. The movement of water in a stream can cause erosion, transportation, and deposition of sediment, leading to changes in the stream's morphology and the formation of various landforms such as channels, valleys, and floodplains. Understanding fluid flow in running water is important in geology for predicting and managing riverine processes such as flooding, sediment transport, and erosion. So next, running water. The term running water applies to any surface water that moves from higher to lower areas in response to gravity. We have already noted that running water is very effective in modifying Earth's land surface by erosion and that it is the primary geologic process responsible for sediment transport and deposition in many areas. In fact, it is responsible for everything from the tiniest rills in the farmers' fields, such as scenic wonders as the Grand Canyon in Arizona, as well as vast deposits such as the Mississippi River Delta. Sheet flow and channel flow. Even on steep slopes, flow is initially slow and hence causes little or no erosion. As water moves down slope, though it accelerates and may move by sheet flow, a more or less continuous film of water flowing over the surface. Sheet flow is not confined to depressions and it accounts for sheet erosion, a particular problem on some agricultural lands. In channel flow, surface runoff is confined to through-like depressions that vary in size from tiny rills with a trickling stream of water to huge river channels, such as the Mississippi and Amazon rivers. We describe flow in channels with terms such as rill, brook, creek, stream, and river, most of which are distinguished by size and volume. Here we use the terms stream and river more or less interchangeably, although the latter usually refers to a larger body of running water. So next, let's have the gradient, velocity, and discharge. Gradient means the slope over which a stream or river flows. It is expressed in meters per kilometer or feet per mile. Next, velocity, a measure of distance traveled per unit of time or meter per second, as in the flow velocity in a stream or river. And lastly, discharge, the volume of water in a stream or river moving past a specific point in a given interval of time, expressed in cubic meters per second or cubic feet per second. So in this figure, letter A, the average gradient of the stream is 2 meters per kilometer. However, gradient can be calculated for any segment of a stream, as shown in this example. Notice that the gradient is deepest in the headwaters area, where the stream originates, and decreases downstream. In the lower reaches of some large rivers, the gradient is as little as a few centimeters per kilometer. Letter B. The maximum flow velocity is near the center and top of a straight channel, where the least friction takes place. The arrows are proportional to velocity. And letter C. These three differently shaped channels have the same cross-sectional area. However, the semicircular one has less water in contact with its perimeter, and thus less frictional resistance to flow. And now, let's move to the running water learning objectives 3. Discuss the role of running water in modifying Earth's land surface. Running water plays a significant role in modifying Earth's land surface by eroding and transporting sediments, carving channels and valleys, and depositing sediment in new locations. This process is known as erosion and can result in the formation of various landforms such as canyons, deltas, and floodplains. Learning Objectives 4. Explain the difference between sheet erosion and channel flow. Sheet erosion occurs when rainfall or runoff removes a thin layer of soil uniformly from a large area, while channel flow is the movement of water through a well-defined channel or stream. Sheet erosion is often the first stage of erosion and can lead to the development of channels and gullies. Learning Objectives 5. Define gradient, velocity, and discharge. Gradient refers to the slope or steepness of a surface. Velocity refers to the speed of fluid flow. And discharge refers to the amount of water flowing in a river or stream over a specific time period. Learning Objective 6. Explain how discharge is determined. Discharge can be determined by measuring the velocity of water flow using instruments such as a current meter and the cross-sectional area of the channel using methods such as the float method or the area velocity method. The discharge can then be calculated by multiplying the velocity and cross-sectional area of the channel. So for the next topic, let us all hear from Mr. Ampon.
I'm Rins Marquimampon. I'm here to discuss about running water, the continuation of running water. So first, running water erosion, sediment transport. Streams and rivers possess two kinds of energy, the potential energy and the kinetic energy. Potential energy is the energy of position, such as the energy of water at high elevation. During stream flow, potential energy is converted to kinetic energy, the energy of motion. But much of this kinetic energy is used up fluid turbulence, but some available for erosion and transport. The materials transported by stream include dissolved load and the load of particles such as mud, sand, and gravels. Because the dissolved load of stream is invisible, it is commonly overlooked, but it is important part of the total sedimentation load. Some of it is acquired from the streams, bed, banks, where soluble rocks such as limestone are present. But much of it is carried into waterways by sheet flow and by groundwater. A stream's solid load is made up of particles ranging from clay size 1 over 256 millimeter to huge boulders, much of it supplied by mass wasting, but some is eroded directly from a stream bed and banks. The direct impact of running water, hydraulic action is sufficient to set particles in motion. Running water, carrying sand and gravel erodes by abrasion, as exposed rock is worn and scraped by the impact of these particles. The dissolved load is transported in the water itself, but the load of solid particles moves as suspended load or bed load. The suspended load consists of small particles of silt and clay, which are kept suspending above the channel's bed by fluid turbulence. The bed load of larger particles, mostly sand and gravel, cannot be kept suspending by fluid turbulence, so that it is transported along the bed. However, some of the sand may be temporarily suspended by current that swirls across the stream bed and lift grains into the water. The grains move rest the grains move forward with the water but also settle and finally comes to rest, and then again move by the same process of intermittent bouncing and skipping, a phenomenon known as saltation. Particles too large to be even temporarily suspended are traction by um, transported by traction. That is simply roll or slide along the channel's bed. Okay, traction or simply roll or slide along the channel's bed. So learning objectives. Learning objective number 7. Define each of the three types of streams total load. So, as I mentioned earlier, there are three streams total load. First, the dissolved load. The part of a stream's load consisting of ions in solution. Suspended load consists of the smallest particles of silt and clay which are kept suspended above the channel's bed in fluid turbulence. Bed load. The part of a stream's sediment load, mostly sand and gravel, transported along its bed. So next, deposition by running water. Rivers and streams constantly erode, transport, and deposit sediments, but they do most of their geologic work when they flood. Consequently, depositions, collectively called alluvium, do not represent the day-to-day activities of running water, but rather the periodic sedimentation that takes place during floods. Recall from chapter 6. Okay. That sediments accumulate in continental transitional and marine depositional environments. Deposits of rivers and streams are found mostly in the first two of these settings. However, much of the terrestrial sediments found on the continental margins. It is derived from the land and transported to the ocean by running water. So that's how it is. So next, the deposits of braided stream and meandering streams. Okay, a few rivers and streams have single straight channels for some distance, but most waterways are either braided or meandering. Braided streams have an intricate network of dividing and rejoining channels separating from one another by sand and gravel bars. Braided channels develop when the sediment supply exceeds the transport capacity of running water, resulting in the deposition of sand and gravel bars. Braided streams have broad, shallow channels and are characterized as bedload transport streams because they transport and deposit mostly sand and gravel. In contrast, the braided meandering streams have a single sinus channel with broadly looping curves known as meanders. Channels of meandering streams are semicircular in cross-section along straight ridges, but markedly asymmetric at meanders, where they are vary from shallow to deep across the meander. The deeper side of the channel is known as the cut bank because greater velocity and fluid turbulence eroded. On the opposite side of the channel, though the water is shallow flow, velocity and fluid turbulence are less. The positional of sand body known as point bar takes place. The broadly looping curves of meandering streams commonly become so sinuous that during a flood, the thin neck of the land between adjacent ones is cut off, thereby forming a crescent shape or oxbow lake. As we can see, there's an oxbow lake. Where's my yes? Oxbow lakes may be persist for a long time, but they eventually fill in with organic matter and fine-grained sediments carried by floods. So that's how it is. So next, learning objectives. Learning objective number 8. Explain the difference between a braided stream and a meandering stream. The braided stream is a stream with multiple dividing and rejoining channels, while the meandering stream is a stream that has single sinus channel with broadly looping curves. So this is the stream, and this is the braided stream. Okay, the picture. So learning objective number 9. Explain how point bars and oxbow lakes form. The point bars form on the gently looping side of the meanders, where the flow of velocity is lowest, while oxbow lakes will form when it starts out of the meandering or in a river. So I will show you the oxbow lakes. Now it separates from its, you know. So next, floodplains deposits. Plains deposits. So flood floodplain deposits. Streams and rivers periodically receive more than their channels can handle, so they overflow their banks and spread across adjacent low-lying, fairly flat floodplains. Okay, spread across adjacent low-lying, fairly flat or floodplains. Sand and gravel might be deposited on floodplains, where a stream or river bursts from its banks, but much more commonly, the deposits are silt in clay or simply mud. During a flood, during a flood, a stream or a river overtops its banks and water pours into the floodplains. But as it does, its depth and velocity rapidly decrease. As a result, ridges of sandy alluvium known as natural leaves are deposited along the channel's margin, and mud is carried beyond the natural leaves into the floodplains, with air settles from suspension. Another feature found on the floodplains is oxbow lakes. Recall that oxbow lakes are cut-off meanders. So, once isolated from the main channel, oxbow lakes receive water mostly periodic floods, although groundwater may also contribute. When they fill in the sediments brought in by floods and accumulating organic matters, they are called meander scars. Okay, meander scars. Some of which are visible in the upper part of the image in the figure 19. Where's my mouse? The original during floods. Okay, so this is floodplain before, during floods. There, there are many water here, and after flooding. So you know the difference. So next, learning objectives. Learning objectives number 10. Explain how floodplains form. Okay. The origin of floodplain deposits. During floods, streams deposit natural leaves in silt and mud set up from suspension on the floodplain. As you can see in the image here, this is how floodplain form. Okay. So next, deltas. Deltas. Where a river or stream flows into a lake or the ocean, its flow velocity rapidly diminish, and any sediment and transport is deposited. Under some circumstances, this deposition creates a delta, an alluvial deposits that causes the shoreline to build outward into the lake or sea. This process is called progradation. Progradation. The simplest the simplest prograding deltas have a characteristic. vertical sequence of bottom sets beds overlain successively by forest beds and top beds, foreset beds and tops, foreset, foreset beds and topset beds. Okay. This vertical sequence develops when a river or streams enter another body of water where the finest sediment, known as silt and clay, is carried some distance out into the lake or sea, where it settles from the bottom set beds. From bottom set beds. Nearer the shore, foreset beds are deposited as gently inclined layers, and topset beds consisting of the coarset sediments are deposited into a network of distributary channels distributary channels traversing on the top of the delta. Small deltas in lake may have the three-part sequence just described, but deltas deposited along seacoast are much larger, far more, far more complex, and considerably more important as potential areas as natural resources. Depending on the relative importance of running water, waves, and tides, geologists identify three types of marine deltas. So the three types of marine deltas. So this is the three types of marine deltas. So, so first, stream-dominated deltas. Stream-dominated deltas have long finger-like sand bodies, each deposited in distributary channels that prograde, progrades far seaward. So let's identify the stream-dominated deltas. Can you guess it? Ada, finger-like, okay? Hand and finger. So next, wave-dominated deltas. Wave-dominated deltas also have distributary channels, but the seaward margin of the delta consists of the islands revoked by waves, and the entire margin of data brigades. So the wave-dominated deltas is is here. As you can see, this is the wave-dominated deltas, Nile River. So next, the tide-dominated deltas. This is the last three type of deltas. Tide-dominated deltas are continuously modified into tidal and sand bodies that parallels the direction of tidal flow. Yes. So next, learning objectives. Define each of the three types of the marine deltas. So I said earlier, if kinig, stream-dominated deltas have long finger-like sand bodies, each deposited in the distributary channels that propagates far seawards. See geofocus. Wave-dominated deltas also have distributary channels, but the seaward margin of the delta consists of islands reworked by waves and the entire margin of delta brigades. The tide-dominated deltas are continuously modified into tidal sand bodies that are parallel the direction of tidal flow. So these are the three types of marine deltas: stream-dominated deltas, wave-dominated deltas, tide-dominated deltas. So next, last and not the least, alluvial fans. So as you can see in the picture, and the image look like a fan, right? Yeah. So alluvial fans. Alluvial fans is a fan-shaped deposit of alluvium on land known as alluvial fans. So, so this is the alluvial fans. Alluvial fans form the best on lowlands, with adjacent highlands in arid and semi-arid, ah, arid and semi-arid regions where little vegetation exists to stabilize surface materials. So this image is so very accurate. So during periodic rainstorms, surface materials are quickly saturated, and surface runoff is funneled into a mountain canyon leading to adjacent lowlands. In the mountain's canyon, the runoff is confined so that it cannot spread literally, laterally, but when it discharges into the lowlands, it quickly spread out. Its velocity diminishes and deposits ensues, ensues. Repeat, repeated episodes of sedimentation result in the accumulation of the fan-shaped body of alluvium. So next, learning objectives. Explain the difference between a delta and an alluvial fan. Alluvial fans and deltas differ where they are found and characterized of their sediment particles. The alluvial fans are found at the base of raised elevations such as base of mountains where they plains. Deltas, the deltas, however, are found near the mouth of rivers. Yes, that's very true. So that's all for my discussion. So next, thank you for your listening to me, and let's hear from Jamie Ocampo. Let's go.
Good day, everyone. I'm Jimmy Arcampo from Group 11, and I will report about the geofocus. And the first one that I will be tackling about is the Mississippi River Delta, past and the present. As you know, deltas form where a stream or rivers enters a standing body of water and deposits alluvium. However, a developing data may be dominated by waves, tides, or stream activity. The Mississippi River Delta is a classic stream-dominated delta that lies or shallow shelf where it is mostly protected from waves and tides. On the delta, distributary channels propagate so far seawards that they became inefficient avenue of sediment transportation so that the stream abandons the channels and establishes a new one elsewhere. In fact, a result of sedimentation, the entire coastline of Louisiana has built a seawards as much as 80 kilometers during the last 5,000 of years. In addition to abandoning distributary channels, stream-dominated deltas periodically abandon entire deltaic lobes. The Mississippi River is currently depositing sediment on a single lobe, but the entire delta is made up of several lobes that formed during the past few thousand of years. In point of fact, where it is not for the efforts of the Army Corps of Engineers, the currently active Balais lobe may have already been abandoned. During the devastating flooding that took place on the lower Mississippi River during April and May 2011, the Corps of Engineers deemed it necessary to divert much of the Mississippi River into the Atchafalaya River at the Morganza Spillway, so as to protect lives and prevent major flooding in Baton Rouge and New Orleans. If the Mississippi were to abandon its present course, it would follow the Atchafalaya River and discharge into the Gulf of Mexico about 100 kilometers west where it is does now. Although such avenant An event would be economically catastrophic for New Orleans. The river would simply continue to build its delta. But in an area that is occupied long ago, stream-dominated deltas grow seawards by progradation. But in the case of Mississippi River, flood controls project now traps much of the sediment so that it no longer reaches the delta. As a result, the delta is losing. We have here the past and present of the Mississippi River. So as you can see, we have the basement, wetland, mud, so leaves. So as you can see, wetland, we have a smaller wetland now, and also the coastline. As you can see in the delta today, that the old coast, we have here the old coastline, and also the river. Few thousand years ago, we have many rivers that connects into many areas, and as for today, we have only one river. Let's go on. Can floods be controlled and predicted? While floods cannot be completely controlled or prevented, their impact can be reduced through proper management and prediction. Flood control measures can include building levees or flood walls, improving drainage system, and implementing land use practices that reduce the risk of flooding. These measures can help to control the flow of water and reduce the risk of damage to property and loss of life. Flood prediction is also an important aspect of flood management. By monitoring weather patterns, river levels, and other environmental factors, experts can make predictions about when and where floods are likely to occur. This information can be used to alert people in affected areas and to take preventive measures to reduce the impact of floods. Overall, while floods cannot be completely controlled, the use of flood control measures and flood predictions can help to minimize their impact on people and communities. When any waterways receive more water than its channel can handle, it floods, occupying parts or all of its floodplain. Flooding is a fact of life, but there are several practices that can protect people and their property and minimize its impact of floods. Unfortunately, none of these measures is land along its margin due to wave erosions and more importantly to compactions. So deposits, especially mud, compact under their own weight, and thus the surface subsides and the sea invades the area where subsidence takes place. Geologists estimate that during the past 4,400 years, the region has subsided about 12 centimeter per century. For example, a large part of New Orleans lies below sea level because of subsidence. Much of the city is located between Lake Pontchartrain and Mississippi River. So when the Hurricane Katrina roared Asnar in 2005, nearly 80% of New Orleans was flooded and 1,833 people have died. We have here the picture. You can see the New Orleans, as I mentioned earlier. This color, Gulf of Mexico. This is the Gulf of Mexico. You can see the sail of Cypremont, Croco- Crocodile, Tichy, Saint Bernard, Laforchi, Bacumine, and Balaise. These are the place or the country where the flood had go. Let's move on to drainage systems. Thousands of waterways that are parts of larger drainage systems flows directly or indirectly into the oceans. The exception are some rivers and streams that flows into the parts basins surrounded by higher areas. But even these are parts of larger systems consisting of a main channel at all its tributaries, that is, streams that are contribute water to another stream. The Mississippi River and its tributaries, such as the Ohio, Missouri, Arkansas, and Red Rivers, and thousands of smaller ones, carry a runoff from an area known as the drainage basin, a topographically high area called a divide separates adjacent drainage basins. The continental divide along the crest of the Rocky Mountains in North America, for instance, separates drainage in opposite direction. Drainage to the west goes to the basin, whereas drainage to the east eventually reaches the Gulf of Mexico. The arrangement of channels within an area are types of drainage patterns. The most common is dendritic drainage, which consists of a network of channels resembling tree branching. It develops on gently sloping surfaces composed of materials that respond more or less homogeneously to erosion, such as areas underlain by nearly horizontal sedimentary rocks. We have here the five drainage pattern. So the first drainage pattern is the dendritic drainage. So what is dendritic drainage? So a dendritic drainage pattern is the most common form and looks like the branching patterns of tree roots. It develops in regions underlain by homogeneous material, that is, subsurface geology has a similar resistance to weathering, so there is no apparent control over the direction the tributaries take. So the second one is the rectangular drainage. So what is rectangular drainage? Rectangular drainage pattern is it is occur when the rock structures steer streams into a parallel course, which tributaries joining at most right angles. Sometimes the joint pattern in the rocks creates a rectangular drainage. This is similar to the trellised drainage, but the pattern is less distinct. So the third one is the trellis drainage. So what is trellis drainage? A drainage pattern in which tributaries join at a high angle, often approaching right angles, which is common in areas with rocks of different strengths, thus resistance to erosion, and in areas with regular series of faults, anticline and synclines. So the fourth one is the radical drainage. So what is radical drainage? Radical drainage is typical of volcanic cones. So long as they remain more or less intact, erosion to the skeletal state often leaves the plug standing in high relief, ringed by concentric valleys develop in thick layer of ash. So the last one is the deranged drainage. So what is deranged drainage? So a drainage drainage system is a drainage system in drainage basins where there is no coherent pattern to the rivers and lakes. These can form in areas with extensive limestone deposits where surface streams can disappear into the groundwater via caves and subterranean drainage routes. So you know the five drainage patterns. So I will show you the patterns that they are symbolizes. So we have here the dendritic like a root, so rectangular like a rectangle line reverse. So the trellis drainage, we have here the ridges of resistant rock, which is mountains. Then the fifth one is a radial drainage, where we have here a volcano, and the last one is the range drainage, uh, lakes and swamp. So that's the five drainage pattern for the drainage systems. So let's move on for the significance of base level. Base level is the lowest limit to which a stream or river can erode, with the exception of streams that flow into the coast depression in deserts. All others are restricted ultimately to six levels. That is, they can erode to no lower than sea level. because they must have some gradient to maintain flow. So ultimate base level is sea level, which is simply the lowest level of erosion for any waterway that flows into the sea. Ultimate base level applies to an entire streams or river system, but channels may also have a local or temporary base level. For example, a local base level may be a lake or another stream, or where a stream or river flows across particularly resistant rocks and a waterfall develops. Ultimate base level is a sea level, but suppose that sea level drop or rose with respect to the land, or presume that the land rose subsided in the cases base level would change and bring out changes in streams and river systems during the maximum extent of Keystone Glacier's sea level was about 130 and no longer than it is now. Streams adjust by eroding deeper valleys and extending well out onto the continental shelves. Rising sea levels at the end of the Ice Age accounted for a rising height level, decreased stream gradients, and deposition within channels. So the geologists and engineers are well aware that the building a dam to impound a reservoir creates a local J's level. A stream entering a reservoir deposits sediment, so unless drainage reservoir eventually fill the sediment. In addition, the water discharge at the dens is largely sediment-free, but it still possesses energy to carry a sediment load. As a result, a stream may erode vigorously downstream from the dam to acquire sediment load. So we have here an example of the significance base level. So as you can see in the picture, you can zoom it. Erosion, it is the base level of the land or the erosion. Erosion, decomposition, then erosion, then decomposition. So the last one is the graded system. So the next picture we have the graded system. So we will tackle about the graded system. So what is graded stream? I mean graded stream. So a graded stream is one with an equilibrium profile in which a delicate balance exists among gradient, discharge, flow velocity, channel shape, and sediment load so that there neither significant erosion nor deposition takes place within its channel. Such a delicate balance is rarely attained, so the concept of graded stream is ideal. Nevertheless, the graded condition is closely approached in many streams, although only temporarily and not necessarily along their entire lengths. Even though the concept of graded stream is an ideal, we can anticipate the response of graded stream to changes may alter its equilibrium. For instance, a change in base level would cause a stream to adjust as previously discussed. Increased rainfall in a stream drainage basin would result in a greater discharge and flow velocity. In short, the stream would now possess greater energy that must be dissipated within the stream system by, for example, a change from a circular to a broad, shallow channels that would sipe more energy by friction. On the other hand, the stream responds by eroding a deeper valley, effectively reducing gradient until it's once again graded. So the longitudinal profile of any waterway shows the elevation of a channel along its length, as viewed in cross-section figure 11.28. For some rivers and streams, the longitudinal profile is smooth, but others shows the irregularities such as lakes and waterfalls, all of which are local base levels. Over time, these irregularities tends to eliminated because deposition takes place where the gradient is insufficient to maintain sediment transportation. transport, and erosion decrease the gradient where it is steep. So given enough time, rivers and streams develops a smooth, concave, longitudinal profile of equilibrium, meaning that all parts of the system dynamically adjust to one another. So that is the graded system. That's all for part for Jim Ocampo. Thank you.
By the way, I am John Marcos Rizzo and I'm going to report about the evolution of valleys. What is valley? Valley is a low area on land bounded by higher land, and the most of them have a river or stream running their length, with tributaries draining the nearby high area. With a few exceptions, valleys form and evolve in response to erosion by running water, although other processes, especially mass wasting, contribute. The shape and size of valley vary from small, step-sided gullies to those are broad and gently shaping valley walls. Step-walled deep valleys are vast-sized are canyons, and particularly narrow and deep ones are gorges. A valley might start to erode where runoff has sufficient energy to dislodge surface materials and excavate a small reel. Once formed, a reel collects more runoff and become deeper and wider and continues to do so until a full-fledged valley. Graded stem. A stream that has an equilibrium profile in which a delicate balance exists between gradient, discharge flow velocity, channel characteristic, and sediment load so that neither significant disposition nor erosion takes place within its channel. Ang kaning graded stem dai is mo na siya if mag-uwan sa inyo ha, may makita mo ganang murag kanal-kanal nga agian sa tubig. Mo na siya ang graded stem kanang na porma siya tungod sa flow sa water. While ang valley is kasagaran makita ni siya between two mountains, two hills. Dako jud ni siya or dako ni siya nga agianan sa tubig. Next is the stream terraces. Rather than flat surfaces paralleling a stream or river but a higher level than the present day. These surfaces represent an older floodplain that was adjacent to waterway when it flowed at a higher level. Stream race is an erosional remnant of floodplain that formed when a stream has flowing at higher level. As you can see sa picture. Next is the incised meanders. Some streams are restricted to deep meandering canyons cut into bedrock, where they form features called incised meanders. Stream restricted by rock walls usually cannot erode literally, thus the lack of floodplain, and occupy the entire width of the canyon floor. It's not difficult to understand how a stream can cut downward into rock, but how a stream forms a meandering pattern in bedrock is another matter. Because literal erosion is inhibited once downcutting begins, one must infer that the meandering course was established when the main stream flowed across an area converted by alluvium. For example, suppose that a stream near base level has established a meandering pattern. If the land that the stream flows over is uplifted, then erosion begins and the meanders become incised into underlying bedrock. Next is the superposed streams. Water flows downhill in response to gravity, so the direction of flow in streams and rivers are determined by topography, yet a number of waterways seems at first glance to have defied fundamental control. For instances, several rivers in the eastern United States flow in valleys that cut directly through ridges that lie in their path. These are examples of superposed streams, which once flowed on a surface at a higher level, but as they eroded downward, they eroded into resistant rocks and cut narrow canyons, or what geologists called water gaps. Superposed stream, a stream that once flowed on a higher surface and eroded downward into resistant rocks while maintaining its course. So, ang kaning superpose is more siya og kuan waterfalls. Somehow example like waterfalls. In summary, water continuously evaporates from the ocean, rises as water vapor condenses, and fall as precipitation. About 20% of the precipitation fall on land and eventually returns to the ocean, mostly by surface runoff. Runoff takes place by sheet flows, a thin, more or less continuous sheet of water, and by channel flow, which is flow that is confined too long through like depressions. Flow, velocity, and discharge are related so that one changes, the other changes as well. Erosion by running water takes place by hydraulic actions, abrasions, and solution. Braided streams have complex of dividing and rejoining channels separated from one another by sand and gravel bars. Their deposits are mostly sheets and sand and gravel. Because of the unequal distribution of flow velocity across meanders, point bars are deposited on gently sloping inner banks, whereas cut bars erode the outer banks.